Welcome also from my side to the tutorial on neuromorphic computing for edge AI. And thank you very much for the introduction of myself already. Before I'm getting into the actual topic, so maybe it's good to start with the awareness of the situation in the complete semiconductor industry. So what we've seen and follow as everyone follows in the semiconductor industry, the growth in semiconductor industry is dictated by Moore's law. We see the number of transistors per area is increasing by a factor of 2 every 12 to 24 months, and Moore's law is holding already for several decades and still follows until this day. And the same holds for the demand for compute, increases by a factor of 2 every 1.5 to 2 years. However, what we have seen is that like about 10 years ago, the computing efficiency and the amount of data which we have to process and the per invested dollar did not increase anymore. And this is increasing a computing gap. So for about 10 years now, we don't get more compute power for more invested dollars. As this trend is halted already for more than 10 years, there's a big incentive to investigate new computational architectures which increase the energy efficiency over existing architectures. Another trend which created some years ago, or basically similarly 10 years ago, is the emergence of artificial intelligence, AI. So what AI is? So textbooks would say it's defined as the field of study of intelligent agents. So any system that perceives its environment and takes actions that maximize its chance of achieving its goals. That could be a very specific goal. So only the inset of a specific input data from an environment and creating some specific output is already AI. Some more popular accounts use the term artificial intelligence, however, to describe machines that mimic cognitive functions that humans associate with the human mind, such as learning and problem solving. However, this definition is rejected by the large fraction of AI researchers. However, this definition is basically the core of what is neuromorphic computing about. So neuromorphic computing and the aspects of neural structure, activation, or membrane potential is at the core of this and will be also part of this tutorial of the brain-inspired computing by neuromorphic computing. State-of-the-art AI can be divided into various categories, as can be seen in this chart here. We see deep learning, which is a very strong part of artificial intelligence, or natural language generation, natural language processing. These are very attractive and very strongly investigated fields of research. So going for deep learning. So deep learning is, as I said, a very large portion of the AI research field. So various deep learning architectures have been investigated, such as deep neural networks, deep belief networks, deep reinforcement learning, recurrent neural networks, and convolutional neural networks. Behind that is always applications in the fields of computer vision, speech recognition, and so on. Despite the quite simple structure, and even though it already has been known since the 1980s, only by the development of very complex compute systems like high performance GPUs, it was possible to make these systems to use about like 10 years ago. So only by then, backpropagation got accessible as an efficient training tool, and deep learning was able to surpass the human expert performance. So we saw in the last decade, basically, the revolution of deep learning applications. One case of deep neural networks or deep learning is convolutional neural network. And as all deep neural networks, it consists of the sequence of layers between an input layer, which is, for example, an image, and the output layers, which include the features it shall describe, with a large number of hidden layers, which can be, in the case of convolutional neural networks, convolutional layers, pooling layers, and fully connected layers. And at the basic heart of such convolutional layers, we have such an operation which is described by an input, which in the interpretation of neuromorphic computing is the axon, which acts on a synapse, which is described by a weight. And this dendrite of an additional neuron then sums up all the influences or the influences it observes and describes it as a membrane potential in itself, and in the end, and gives an output until dependent on the activation function itself. And mathematically, this is nothing else than a weighted sum operation or a multiply and accumulate operation. And such multiply and accumulate operation can be computational intensive, mainly because we have to call a lot of storage. We have to call a lot of weights, as these neural networks tend to get larger and larger, as we can see here. So deep neural networks evolved over the time, outperforming other classical AI techniques like SVM or Markov chain or decision trees and so on. But AI is now dominated by the attempt to improve the accuracy on standard benchmarks. So scaling up the networks, so networks get larger and larger every year to achieve higher accuracy levels. And a good example for that is the GPT-3 model, which is able to create text. It has like 175 million weights and requires a memory of 350 gigabytes of data. To really train such a neural network, it will take about $12 million for only one application. So it's a very intensive field of work. The successor of GPT-3, GPT-4, is currently even acclaimed to possess 100 trillion weights. So you can estimate that such networks are not running on what we call the edge. Furthermore, with the emergence of such larger and larger AI models in data centers, the energy consumption of data centers is severely increasing. According to the International Renewable Energy Agency, at the current speed, the ICT industry will consume about 20% of the world's energy in 2025. So we need to identify ways to reduce the power consumption of such neural networks. And we hope that neuromorphic computing can be part of that. So why do we need edge AI and edge computing? So such large networks, particularly large AI, as I said, can only be computed in data centers, what we call the cloud. But when the results of such computation and potentially even the input data have to be transmitted from the edge devices, as what can be billions of devices like smartwatch, smartphones, heart trackers, any kind of small electronic devices, and they have to be transmitted from the edge device over the fog node to the cloud and back again towards these edge devices. We have a latency issue. The communication back and forth is just too slow for most of the real-time applications. And furthermore, the power consumption which is attributed to this is detrimental to the work of them as being battery powered. However, when we will really try to implement neural networks on the edge, we see this kind of similar issue because most of the computing systems, microcontrollers as a standard architecture, are separated between storage and computing center and connected via a bus. And this bus gets the bottleneck for such storage-bound tasks, which AI are, which call a lot of weights only to do a very simple operation, which is this weighted sum operation. That means neural networks are computationally so intensive tasks that it actually limits the best bandwidth as well as the energy consumption drives this intensively. So, for example, when we call only a single bit of information from an external DRAM, for example, it can take 10 to 5 times more energy than to just compute something with this one bit. So it seems much more reasonable to combine and together. So, in the very beginning, we are facing an era of halted compute price efficiency. So to overcome this, a lot of researchers expect an era of hyperscaling by innovation on various levels of development in which new materials, new devices, and new system components or system implementations get established to improve the cost efficiency for the compute power. On the materials level, novel materials are currently investigated featuring ferroelectric properties, phase transition or metal insulator phase transitions, spin transfer or spin orbit torques, as well as resistive switching, with the target to reach a large range of memory states inside them. On the device level, novel emerging devices are explored to feature more brain-like properties like STDP, multi-bit process properties, or a specific retention behavior which is inherent to neurons. So we try to find devices, materials, and systems which get closer to the behavior of the human brain. In my group, we focus on ferroelectric implementations using ferroelectric field effectors for in-memory computing. However, a very broad community of researchers is working on a lot of memory implementations such as resistive RAM, PC RAM, and so on as well. So what we try to do is basically bridge the gap which we see in the energy efficiency between standard architectures, standard systems like GPUs, FPGAs, or even ASIC implementations. Still, the power efficiency of these systems compared to what the human brain can do is orders of magnitude away. What we try to do is we try to bridge this gap with in-memory computing and analog computing implementations and other features which are implemented in neuromorphic computing, which I will discuss a bit later. So, but look into in-memory computing. In-memory computing is an approach where certain computational tasks are performed in place in the memory itself, organized as a computational memory unit. As given here with a schematic by Abu Sebastian of IBM Research, this is achieved by exploiting in tandem the physical attributes of the memory device. As I said, they're array level organization, so the macro, the peripheral circuitry, which includes, for example, ADCs, so analog digital converters, sense amplifiers, or similar, as well as the control logic to distribute the information. Any computational task that is realized within such a system could be referred to as in-memory computing. However, the key distinction is that at no point during the computation is the memory content read back and processed at the granularity of a single memory element, which means a performance similar like a non-volatile memory array. This latter scenario, where in addition the processing is performed in close proximity to the memory array, would be viewed as near-memory computing. So I skipped the part that next to in-memory computing, there are also ways to put the memory quite close to the processing element. However, this is not as efficient as in-memory computing. Besides alleviating the costs and latency and energy associated with data movement, in-memory computing also has the potential to significantly improve the computational time complexity associated with computational tasks. This arises mostly from the massive parallelism afforded by a dense array of millions of memory devices performing the computation. It is also likely that by introducing physical coupling between the memory devices, we can further reduce the computational time complexity. By blurring the boundary between the processing and the memory units, we gain significant improvement in the computational efficiency. The memory options we can implement here reach from memories like SRAM, static random access memory, DRAM, flash, or resistance-based memories like RAM, PCRAM, or STT-MRAM, and hence constitute both volatile and non-volatile memory solutions. Here's a summary table of the suitable memory technologies to be used for in-memory computing. It reaches from standard memory technologies like SRAM, floating gate flash, over memories which are still under development as emerging or more developing memories such as embedded DRAM, Sonos flash, at least in very advanced nodes, RM, PCRAM, STT-MRAM, as well as a couple of ferroelectric memory concepts. The main difference in the implementation for in-memory computing are the differences in the on and off resistance. So for example, for STT-MRAM, this on-off ratio is very small, typically only in the range of 2, which makes it very difficult to implement that into in-memory computing. Particularly the transistor concepts like flash or Sonos flash or ferroelectric transistors have very high on-off ratios, which make them interesting for the implementation. Furthermore, it's interesting to identify the cost which is connected to using these memories. So how many additional masks have to be used to include this, as well as the cell size of them. So how much weights can we really store in such a memory macro, which is detrimental and very important for the use for in-memory computing. As I said before, all networks which are currently developed are growing at a high speed, and if we want to limit this for edge implementations, we have to see that a high storage efficiency and a very high storage can be achieved. Furthermore, it's interesting what is the write time or write energy which we need. So some cells have extremely low energy used per write cycle, particular SRAM or FFET, and are having a very small latency, which is very important for the overall power consumption. So for SRAM, and as well FIFET, we have latencies which go into nanosecond region, which means it's possible to read out the state in up to gigahertz ratio, whereas a lot of other memory cells have much smaller, much lower latency. For example, the case of floating gate flash, you can only read it out in the millisecond range, which makes it energy consumption-wise quite difficult to be used. Furthermore, endurance is an important factor. So the more you can write this memory element, the larger or the more you can reconfigure the neural network inside. So either between in different inferences, so between running the accelerator or running the complete neural network, or even between different layers in the neural networks. However, this is also connected to power consumption to write the cell. So SRAM and DRAM in this case, basically unlimited endurance, unlimited cycling possibility, whereas all the other more non-volatile memories have limited endurances. And yeah, all the volatile memories mostly have shown a retention of their states to be about 10 years, which makes it possible to store the weights even under switching off the edge device, whereas the volatile memories like SRAM or even DRAM, which needs a refresh over time, have a static leakage in their, or static power consumption over their use, and lose their memory state under switch off of the edge device. So how is in-memory computing done for example, convolutional neural networks? Very quick, we have an input feature map, which could be an RGB image. Here we have 3 images, which are captured by a camera. We have kernels, which are describing the convolutional operations, and we run all the convolutions over the input feature map over this RGB image and get a convolution output at every pixel, which we call the output feature map, and do these convolutional operations for every pixels, and that's basically what is needed for one convolutional operation. How is in-memory computing now realized? In general, a very basic scheme is constituting of the digital analog converter, an array of these memories, volatile or non-volatile memories, and an input line and the output line, which accumulates the current, which is then sensed and digitalized with an analog digital converter at the end of this drain line. Typically, and that's what we call crossbar. A lot of these crossbar arrays are implemented in the system, and which is connected to a digital interface controlling such a system. In-memory computing is not only interesting for deep learning applications, but for a very broad range of other types of calculations. So the computational primitives reviewed in the memory devices section have been already applied to a wide range of such application domains, ranging from scientific kind of computing, so solving linear and partial differential equations, which require very high precision, to, on the other end, stochastic and computing or security operations, which and are enabled by very high imprecision or randomness. So a high level of overview of the main applications is given here. In-memory computing can be applied both to reduce the computational complexity of a problem, as well as to reduce the amount of data to be processed by performing computations inside the memory array. The problem that could benefit also very strongly from the complexity reduction by in-memory computing are also so-called NP-hard problems, which are involving combinatorial optimization. These are problems which are typically solved under, for example, quantum anneal operations, etc. So data-centric applications in machine learning and scientific computing benefit very strongly from this parallel memory access. So this is one implementation how AI can be accelerated. Here I want to give a comparison of the current AI hardware prototypes or early products we see so far. So there are implementations which are relying still on GPU kind of implementations. Some are working on analog crossbars and feature particularly high energy efficiency values. These are working on electronic implementations of such a crossbar. However, also some companies are working on optical crossbar implementations, which we will look into, as well as implementations which feature wafer scale integration. So have a look into these. So photonic circuits are well suited to do such high performance implementation for neural networks for basically two dominant reasons: interconnectivity and the linear operations. So connections between pairs of artificial neurons are described by a scalar synaptic weight, so a primary memory element. The layout of the interconnections can be represented again by such matrix vector operation, where the input to each neuron is the dot product of the output from the connected neurons attenuated by a weight vector. The memory cells in such photonic ICs are typically interferometers or Mach-Zehnder interferometers. What photonic ICs are interesting for are particularly real-time operations, because running a complete neural network is extremely fast in photonic ICs, so real-time operations can greatly benefit from such implementations. A drawback of photonic ICs is basically the limited density of memory cells, as memory cells or such interferometers typically are in the range of hundreds of microns. Nevertheless, these implementations are interesting because they are extremely fast and can be also very energy efficient, because the energy which is consumed over the weight cell is very, very small. On the other hand, I wanted to show you wafer level integration. Here is an example of such an implementation. So it's using wafer level integration and using much larger area of a wafer than typically used in chips. So here's an comparison between the largest GPU which has ever been created, and this to be a chip which uses wafer level integration. That's a company called Cerebras, which is using these. And with this, you create a super chip, so to speak, of, like in this case, 400,000 of cores being connected, and with an extremely large number of on-chip SRAM, here in this case 18 gigabyte. However, there's a reason why chips are typically not that large so far, mainly because you have strong yield issues or variabilities from die to die, and it's possible to basically extract these devices from a wafer, which is not possible in such a extremely large Cerebras chip. So it's vulnerable basically to die yield. Nevertheless, it is extremely strong in the way that you have much more memory bandwidth in such a system, which is right away connected by wafer level integration. In fact, you have 10,000 times the memory bandwidth than in conventional systems. Okay, so, but now maybe go a step back from these super large chips. We go in first to super small chips, which can then maybe also used more in edge-related environments. So whereas artificial neural networks, such as convolutional neural networks, emulate the abstract brain-inspired computing architectures by digital and time-multiplexed implementation. The spiking neural networks use the time evolution of the physical elements in the system and their dynamics to implement the computation. So what we basically see is the physical system we imply is the algorithm. Spiking neural networks are deeply rooted in the neuroscience and in neurobiology, and the description of neurons and synapses of biological system is the basis of the implementation, and it tries to use the properties of all kinds of devices, silicon implemented memristive devices, to directly emulate similar neural properties as we see in actual biological system. And so it combines analog and also asynchronous digital and logic circuits to really create a system that follows very close to brain computation. So it yields basically a very specific device, which is quite optimal for edge computing. So what does a spiking neural network consist of? Neurons. So what are neurons? More precisely than what we described before. So the neural interactions are actually time-varying electrochemical dynamics that give rise to the brain's diverse functionality. The dynamic behavior, in turn, are governed by the actual voltage-dependent opening and closing of charge pumps in the specific ions of sodium or calcium. So in general, a neuron maintains a specific resting potential across its cell membrane by maintaining constant charge gradient. Incoming spikes to a neuron leads to an increase in its main membrane potential, which you can see here, and to increase in a leaky integrate manner until the potential crosses a certain threshold, until the potential and emits a spike then. And that's what we call a leaky integrate and fire neuron, or integrate and fire neuron. For leaky integrate and fire neuron, the membrane potential is leaking away over time as long as there's no incoming spike over time. So having a knowledge on the generic qualitative nature of the neural functionality, it is obvious that the resulting model describing the biological neuron would consist of a bit more complex dynamic equation than such a leaky integrate and fire neuron. In fact, the more detailed mathematical model is the Hodgkin-Huxley model, and it describes very well the brain neuron, which we see. And the spike response model, which has been developed, is really closely matching the biological neuron. However, implementing such a model in hardware turns out to be quite complex, as such that hardware implementations so far mostly focus on more simplified neural net models, such the leaky integrate and fire, or the only integrate and fire model. As furthermore, stochastic firing neuron models have been used, which is described here. So the next we have synapses. So what's synapses in more biological terms? So the information in biological systems is governed by the transmission of the electronic pulses between the neurons, the adjacent neurons, through the connecting bridges. So that's the synapse. And the synaptic efficiency represents the strength of the connection through an internal variable. So that's basically what in, say, generation 2 neuromorphic computing in deep neural networks has been termed weight, right? The strength of connecting to adjacent neurons. However, also the synaptic efficiency representing this strength can have a specific plasticity. So neurochemical changes can induce changes in the synaptic strength by permanently manipulating the release of neurotransmitters and controlling the responsiveness of the cells to them. And this is basically the base of learning rules. So such plasticity is believed to be the fundamental basis of learning and memory in the biological brain. So from the neuromorphic perspective, the synaptic learning strategies can be classified in two specific ways. So first, unsupervised learning and supervised learning. So that's something which are two strategies which are currently used in hardware implementation. As obviously unsupervised learning is what we see in biological systems. So for supervised learning, we use parallel arrays of processing elements to maximize the grain parallelism and to increase the energy efficiency by co-localizing the memory and the computation. Using the physics of the electronic device to emulate the neural dynamics and exploit all the properties of the transistors, memory cells, and memristors. While for unsupervised learning, we actually can change the synaptic efficiency over time. And the very simple rule would be the STDP rule, the spike-dependent plasticity rule, which is proven to not be correct for biological system, but is a way to train the synaptic efficiency over time. So what are the complete primitives of the brain-inspired computing? So we already talked about things which are somewhat mature, in-memory computing and analog computing. We talked about plasticity, so learning rules which can change the synaptic efficiency. We talked about parallelism, which makes in-memory computing very efficient. So having a lot of in-memory computing, processing elements or crossbars, and having a very large parallelism makes neuromorphic computing systems extremely efficient and powerful. We did not talk too much about probabilistic computing or computing which only is based on likelihood, but also this is a major technology, or it's clear how we can implement it. But there are parts in neuromorphic computing which are still not completely understood. These are sparsity. So the possibility or the ability to see changes with only a very small amount of spikes. It's still not clear how we can scale very small systems. So really can harvest the parallelism that can be or is already used in deep neural network accelerators. And we also cannot harvest so far the possibility of nonlinearity and causality, which we can see in the brain. So there's still some parts in the research on neuromorphic computing which has to be carried out. But to really get neuromorphic systems on for example, edge AI applications, which can achieve the energy efficiency we can see in brains. But as soon as we get these challenging questions done, neuromorphic computing will be a very important part of the computing world in end systems. And with this, I would like to thank you for attending the tutorial.